Welcome to the third video in my proof by induction divisibility series. In previous videos we've seen true for k and then true for k plus 1, i.e. all integers bigger than our base case. In this video I want to introduce you to a new idea that we haven't quite looked at yet, and that's when we're not quite looking at all integers but maybe a set of the integers, such as all odd numbers or all multiples of 3 or all numbers 1 more than a multiple of 3, and the idea on how we can deal with them. We could also use this to do proofs for all negative integers by finding a base case and then doing k minus 1. So the idea is we're going to do exactly the same thing. We're going to do our same normal base case. What we're then going to do is we're going to do our assumption as normal. The only difference is our consideration. We're not considering the number after k, we're considering the number 2 after k because it's the next odd number. So our consideration will be k plus 2. Now, you could reformulate this. You could say, well, let n equal, 2a plus 1. So let n be an odd number, and then you can do regular induction. But I think this way is better because it gives you more sort of a wide spectrum of problems you can attempt. So let's have a look. So let's have a look at our base case. So base case, n equals 1. We get 1 to the 4 minus 1, which is 0, which is the same as 16 times 0. We saw in the previous video why this makes 0 divisible by 16. Next, we're going to do our assumption step. So we're going to assume true for n equals k, i.e. k to the 4 minus 1 is equal to 16a, where a is an integer. Next, we're going to move on to considering the k plus 2 term. So we're going to consider n equal to k plus 2. So not the number after k, but the number 2 after k, so the next odd number. So we're dealing with k plus 2 to the power 4 minus 1. Now, we saw in previous videos that our whole idea after this was to involve the assumption. What we would do is we'd get one part of the assumption on one side, and then we'd try sub that into this expression. So I'm going to get k to the 4 on its own. That gives me k to the 4 equals 16a plus 1. And now when I do binomial expansion, what I'm going to be able to do is I'm going to be able to combine these, bring in ia. So we get k to the 4 plus 4 choose 3, k cubed 2 to the 1, plus 4 choose 2, k squared 2 squared plus 4 choose 1, k 2 cubed. Finally, plus 2 to the power of 4, and we can't forget about our minus 1. This all simplifies to become k to the 4 plus 8k cubed plus 24k squared plus, well, we've got 8 times 4, so 32k plus 16 minus 1, like so. Now, what we can now do is we can replace our k to the 4 term. So this is 16a plus 1 plus 8k cubed plus 24k squared plus 32k plus 16 minus 1, or we could just rewrite this as 15. Now, we said before that what we like to do is we like to group all of our divisors up on the left side. So when it's done, we put it on the left, and then we only have to deal with the stuff on the right. So this has a multiple of 16 is 16a. So we can write this here as 16 times a. Grouping this up with the 15, we get a 16, so we get a plus 1 when we take the factor of 16 out. And we have a factor of 16 here, so we get plus 2k. What's left is plus 8k cubed plus 24k squared. So now our final goal is just to factorize all of this as much as possible and see if we can make a deduction from it. So we leave this as is, plus, well, there's a factor of 8, there's a factor of k squared. So that's going to leave us with k plus 3. Now, this is certainly a multiple of 16, but what about this? Well, it's already a multiple of 8, so we just need to show that this is a multiple of 2, no matter what k is. And I said before that when you get to a stage like this, your first step is to factorize as much as possible. Once there's no more obvious factorizations to do, if we still haven't got to our answer, we need to look at proof by exhaustion. So we're trying to show that k squared times k plus 3 always has a factor of 2. So if k is odd, well, why would there be a factor of 2? Well, k plus 3 is then even. Okay, nice. And if k is even, well, we have k squared. So k squared is even. So we have a factor of 2, no matter what case we look at. So, in all cases, this is divisible by 16. Because it's already divisible by 8, we just need to show it's divisible by 2, but if k is odd, it's divisible by 2. If k is even, it's divisible by 2. So we're done. So, as true for n equals k plus 2, when true for n equals k, and true for base case n equals 1 by mathematical induction, it must be true for all odds. For all odd numbers. And that's it. That's our proof. That's it completed. I hope this was helpful. I hope you can see this is a much more tricky example. But the idea remains. We first do the base case. We do the assumption. We do the consideration step. On the consideration, we need to somehow involve our assumption. Once we do that, we want to put all of our finished terms, as in we can already see they have a multiple of 16, we want to put them on the left. All of the terms that aren't finished, we keep them on the right, and we're just going to try to factorize as much as possible until it's obvious that we're done. So like we saw in this example, we factorize it as much as possible. Only thing left for you to do is proof by exhaustion. Got to show that there's a factor of 2. But I hope this was helpful. In the next video, we'll have a look at proof by induction for inequalities.